Welcome to the ninth episode of the Kern Competence podcast. Today I'm once again joined by Simon. Simon, welcome.
Welcome, Marvin. Thank you.
How are you, Simon?
I'm absolutely great. So it snowed roughly 20 centimeters tonight. Now the sun is coming out. Everything is white. It's end of November, the most stressful time of the year actually for Kern. But besides that, couldn't be better.
Yeah, nice. I think you had a little bit more snow in your village than I had where I live. But here in Eschenlohe, it's absolutely beautiful. We're sitting in your office, and when you look outside, it's just like winter wonderland. So that's really nice.
Yeah, there's danger around. This is our, you don't say janitor, we call him the facility manager. It's Jakob Gantner. I think he's 67 years old in the meanwhile, and he's driving a big truck, and his first mission is getting rid of the snow. And if you're in the way, you're in a danger.
Yeah.
So he's going to shout at you and honk at you. And
The Bavarian weather report yesterday reported danger for life and body because of the snow, and I was like, it's not gonna snow that much. But when I saw Jakob when I arrived today, I was like, oh, terrible mortal danger.
yeah, and he has a really red head, and yeah, he's fuming.
Heating up the cabin.
Yeah.
Okay, today's subject, we want to talk about technology, but for once, not about machine technology.
Yes, I think so. Today it's more about you and you answering questions that hopefully I have prepared accordingly. But as an introduction, I think we covered that multiple times before, that the magic about Kern is not just the machine. So we put a lot of energy into the technical differentiation. We invest a lot into usability and things like that. But also a very big part, and the one that makes the biggest differentiation, I think, is technology, is process, is really transferring know-how from us to the customer, and the other way around, learning and improving. And one of the, if not the most crucial part of that is the technology, is the processes, is new materials, is everything that has to do how they use the machine properly. And we have the applications department, which many others have too, but in our company there's a special part that is called future technologies. And perhaps, Marvin, you can tell us a little bit more about that objective, about the mission that we're trying to tackle with that.
Yeah. We found a couple of years ago that by having some body of knowledge that other machine tool companies doesn't have, and the willingness to share this with the customer, we are actually able to sell machines. This is kind of surprising because, you would expect our customers to come here and want to buy the best performing machine, and a lot of them do. But sometimes it's also just that they see we know more about how to manufacture a part than they know. And we decided to do like a strategic department chasing these new technologies. I often explain it to customers that we have like a strategic development, which is headed by Matthias Fritz. They are in charge of developing like the next gen machine. So the machine is built by them. And then we have like an operative development, which is if a customer needs like a new aggregate or a new feature to an existing machine. So they kind of take care of the life cycle of the machine. And what we didn't have until a couple of years ago was some department or someone looking into strategic advancement of everything that happens once the machine is fully built. So basically the state our customers experience the machine. And I think there is a huge potential there, because if you look at a good part, obviously, and we wouldn't exist, one requisite for a good part is that you have a good machine. I think we can agree on that. If the machine is not like running smoothly, and if you're
Repeatably.
yes, all of these things, then you're not going to have a good part. And another large part is, of course, the tool. There's good tool makers out there and there's not so good tool makers out there. But something I find interesting is if you take, let's say you take a super high quality Japanese tool and they have some fantastic tools and you run it with the manufacturer's suggested cutting data, you will get decent tool life and you will get a decent result. But if you change the feeds and speeds and maybe the way you use the tool, you can get a part which is multiple times superior.
But this is an important thing and very interesting. So actually, you don't approach that by trial and error, but you put a little bit more science into that. Let's put it like that. How do you usually do that, and what equipment do you need? What are you using, and how do you approach those things?
I mean, we have to backtrace one thing because you said trial and error and I mentioned tool manufacturers. And a lot of tool manufacturers are probably going to hate me after the next statement, but this is what the majority of them is doing. If you're very lucky and they are like super proficient, they are doing stability cards. So they set up a test plan, they execute this test plan and they look like, when is the tool failing? They go a little bit below that value and then they suggest this is the cutting data. Now, this is basically trial and error. They are testing something and looking at the result, and sometimes it fails and sometimes it's successful. And I decided a couple of years ago that I don't want to do my experiments this way. Because if you, for example, look at milling aluminum, at a certain point of your cutting speed, the behavior changes drastically. So if, for example, if your cutting speed goes above 1000 meters per minute cutting speed, you are in what is called a high-speed milling regime. And then the majority of the heat doesn't go into the tool or the workpiece, but into the chip. Now, if you look at those clever books that tell you how to mill, they usually suggest milling aluminum at 180 meters. And if you have like a high-quality DLC-coated tool, they tell you 350 meters. That is because every machine can kind of execute this, and it's a proven concept, but then you need coolant. If you go above these 1000 meters, if you enter like the high-speed regime of aluminum, you arrive at a state where you don't need coolant, and you can suddenly mill aluminum with nearly no tool wear, completely dry. Now, this is a massive game changer because you are more productive, you get better surface finishes. This is one of the reasons all of our parts are so shiny, because we mostly mill in this high-speed milling regime. But the discovery for this wasn't trial and error. This wasn't someone just like trying out 1000 meters. This was a scientific basis. They looked at a phenomena. In this case, it has to do with sonic speeds in the material, it has to do with dislocation mobility in the material, it has to do with phonon transmission in the material. So it's a lot of material science concepts. And then someone, it was in the 1930s in Germany, a guy called King, he decided, okay, he wants to chase that effect and make it visible in milling. So it's not by starting with a set experimental plan, but it's by starting by seeing, identifying an effect and trying to create conditions to provoke that effect. And I think this is the drastic difference between how usually cutting data is developed and how like our future technology does it.
Okay. Looking a little bit deeper into that. So there's one big example that I think everybody knows that we're carrying forward, which was a big breakthrough not only for us, but also for our customers, which is the ductile cut in hardened ceramics. Can you explain us a little bit more in detail? How did you actually come to that idea, and how did you approach the whole thing?
Yeah, I mean, I think it was mostly you who came to me 5 years ago, and you were like, hey, we have a really big project and we want you to do it. And this was at that time by far my largest project at Kern. Before that, I was working on stuff for like 1, 2, 3 months. And you were like, this could easily take 2 years of your time. And the requirement for that project came a little bit from our contract manufacturing. They were getting more and more RFQs for ceramic parts and know-how on how to manufacture these parts was missing in the company because, well, it is difficult to manufacture hard ceramic parts. And we approached this first in like a scoping review. So we did a little bit of like Googling, like manufacture ceramics, and you don't find a lot there. And then we kind of looked like tool manufacturers that were advertising ceramics and then invited them and had them show off their tools. And one tool manufacturer that is very well known is 6C Tools. And their CEO and founding partner Jens Boos, he came in with a couple of tools. And we had like a small disc of ceramics and we just like milled into it. And I mean, the ceramics we milled back then, it was silicon carbide. It's about 3.5 times harder than regular tungsten carbide, from which milling tools are made. And I have to say, I mean, this was 5 years ago. His tools managed to mill into the ceramics, but also the results were like super bad. We were milling a slot and the breakouts on the side of the slot were larger than the slot itself. So it's kind of like, wow, okay, I could probably chisel this. And if you know me, I'm really bad with hand tools. So me saying I could chisel this is a really hardcore smackdown. And then we first did like proper design of experiments. So we set up experiment plans. This is kind of a little bit like trial and error, but you think before starting to do it, you think about what you're doing. And we executed these trial plans and we got it to a, I would say, decent result. Like the breakouts were getting smaller than the features you were milling and productivity went up and tool life increased. And I think this would have been the point where the majority of mechanical engineering companies would be like, okay, now it's working. We can produce customer parts with this. This is fine. I was unhappy with the situation back there. I think this is probably the most annoying thing you and I have in our interaction, that I'm so hungry to change something, so driven to change something, that I'm often sitting in your office and just like complaining about the state of things.
Oh yeah, know what you're talking about.
Yeah, exactly. And back then I was like totally unhappy, and I was like, okay, seriously, there is cooler stuff. And my background is not in mechanical engineering, and my background is not in CNC machines. I mean, I'm in German, you would call me an autodidact, and I'm guessing it's the same word in English. Everything I know about CNC machines is self-taught. I never had professional formation in that regard. But my professional background is in material science, and it's fascinating. Like the industry, our industry has been trying to manufacture hard ceramic parts for, I would say, 20 years now, like really focusing on doing it. And they were happy with basically what they achieved on the first try. You take an immensely hard particle, diamond, and then you grind away and you have a brittle material removal. The diamond is so hard, it enters the material and then it breaks off chunks of the material, and then you just use smaller and smaller diamonds, and then your surface gets smoother and smoother because the breakouts are smaller and smaller. And they were happy with that. But in the 1950s at the University of Vienna, they were doing a project on sawing stone salt. Just like taking sawing blades and huge chunks of stone salt, and they wanted to improve productivity on this and like tool lifetime of the saw blades. And when they looked at the cutting surface of the saw, they sometimes found areas that kind of looked molten. Now, the melting point of salt is really high, and with like an HSS saw blade, you're never going to reach that. Like the saw is going to melt down before you reach the melting point of salt. And then they discovered, okay, even if you have a brittle material, maybe there are some conditions with which you can find a ductile behavior. Now, ductile behavior is kind of like the opposite of brittleness. Brittleness is you take a ceramic plate, you drop it, it breaks into chunks. And ductility is like that the material behaves in a plastic way. You take a small bar of aluminum and you bend it, and it doesn't break, but it bends. That's ductility. And back in that ceramic project, I was really unhappy with the quality we achieved because it was just like, it was the state of the art. Okay, I mean, this is kind of funny. I was
better than a little bit,
yeah.
but not really a breakthrough.
yeah, it was just like it wasn't something new, and I wanted it to change. And this ductile behavior of brittle solids has been researched a lot since the 1950s. And there was a lot of major research in France in the 1970s where they actually managed to describe the effect on a quantum level. And then I would say in the early 90s, people were able to make it happen on a diamond turning lathe, so an ultra precision machine. But no one has been able to make a ductile regime appear in a milling machine because, well, the requirements on a diamond lathe can be met, but a milling machine can't match the level of precision or the way they fabricated these parts. And then I remember very clearly it was like a Friday afternoon. I waited until a Friday afternoon, so the company was kind of empty. And I was like, okay, today either the machine is going to die or I'm going to find a ductile regime there. And one of the prerequisites to achieve ductility is temperature-aided ductility. So if you increase the temperature of the ceramics, they might become ductile. It's not that they are melting, but it's just like a lot of the effects that appear, like the physical effects that appear in ductility, they improve if you increase the temperature. So I was taking a really large insert cutter, like 50 millimeters. And on our machine, there's on like the control board written maximum VC cutting speed, 2000 meters. This has safety reasons, because if something breaks, you don't want it to shoot out of the enclosure. So our enclosure is safe until 2000 meters cutting speed. I completely ignored that. I used that insert cutter with solid diamond inserts, and I went up to nearly 6,500 meters cutting speed. Now you have to imagine that's an enormous cutting speed. Most machines are not able to achieve that because the spindle is just not quick enough. It's basically 50 millimeters rotating, I think, at nearly 40,000 RPM. So that's machine was also humming a little bit. That machine is now in our contract manufacturing, so everything's fine.
Doing good.
Yeah. And that machine had oil coolant, and I remember when the cutting edge was entering the material, you could see it glowing white. So it had like flood coolant oil on, that insert cutter humming like a wasp net, and every time it was taking like 5 microns off the part at 6,500 meters VC, the cutting edge was glowing white. That was a little bit scary. And I remember Matthias standing next to me. He, like our head of development, he was around and he was looking what I was doing because he could hear it to his office. And then I decided, like, Matthias, maybe we stand behind the sheet metal enclosure and not in front of the door with the glass cabinet. Yeah, and then the toolpath ran its due, and I opened the enclosure and sprayed off the oil of the part, and the results were amazing. Instead of like a smooth but matte surface, you had a glossy, shiny, mirror-like finish. And I was kind of like, then I knew, okay, ductility is possible on a milling machine. Now, for our customers, and I think this is really the point where we differ from a university in what we are doing in my department. A university would have published 2 papers about this, would have gone to conferences, would be like, hey, we managed to get ductility working. And I would say my cross with universities is they are happy at that point, but we kind of, well, we are a company. We at some point we need to earn money, and this means customers need to be able to use that technology. And 6,500 meters VC is not something customers should ever consider on the machine. So obviously I had to translate it into a usable set of feeds and speeds that a customer could use on the machine.
Okay. And this was the point where it started to get a little bit more scientific, at least from my point of view. But I think what you said is a very important point. So in a company like ours, there's always a fight between, for example, what we want to investigate, what we want to develop, and what is relevant to the market and to our customers. And on the other hand, there's also this idea of, I should have phrased this, what the customer really articulates as a need, and a point where things that actually might be relevant or are relevant are not articulated anymore, if you know what I mean. So articulated and unarticulated needs. So if you know the customer good enough, you can actually not just do the next, but the second to next step. And I think this was very nicely shown in the ceramics project, because of course you were interested in that. It was relevant at that time, but actually nobody ever showed up and said, we need a part in silicon carbide. We want to create or mill features like this and that, and this is the exact requirements. This is something that we came up with, and which puts you in a little bit of a also challenging situation, and we often have that as Kern. So if you're able to do things, like for example also in contract manufacturing, this is a wonderful thing, but not everybody is going to jump on it right away. Because the first thing that you need to do then is to tell the guys designing parts that this is possible at all. So you have to do marketing in the sense of educate people. So this is doable, and not just on a laboratory scale, but we can really automize and productively produce parts in a certain quality that you, from the experience you have in the last 20 years, would say it's not possible. So that is an important step. And also, therefore, I think the whole communication also you did with parts, etc., was an important step in really making or creating the awareness that we actually found something that is relevant also on a second to next step in the parts design you will see for the future.
Yeah, I mean, you're completely correct. People have been so used, because they've been doing it for 20 years, on how you manufacture ceramic parts. It's basically grinding. Grinding works nicer with large tools. So they don't do small features. They don't do internal features. They try to design the parts in a way that everything can be accessed really easily from the outside with a large grinding wheel. And when we discovered that ductile regime of cutting ceramics, and then kind of went to the market, our first idea was like, okay, well, you can't patent process in Europe. So this is something we kind of need to protect, because it's very expensive company IP. But at the same time, let's do contract manufacturing. That was basically our idea back then. And we started by publishing a couple of application notes about how this new technology is going to improve part technology and shows tremendous potential for productivity. And then people came to us with like parts that are easily diamond crowned on like a rotary grinder. And they were like, hey, we read your article. Can you do this part cheaper? And well, we looked at it and we discovered like, no, obviously we can't, because nothing beats grinding in terms of monetary expenses. It's like grinding tools are relatively cheap. They're very large, huge material removal rates, so everything's fine. And it really took us some time, and really talking to customers and listening to them, and then kind of being like they were showing us parts, and we were like, okay, this is a cool part, and you're able to manufacture it, but why isn't there this feature on the part? Why don't you do a slot there? This would improve the use of the part. And they were like, yeah, no one can do that slot. We're like, hey, we can do that part. Can we talk to your engineers? So the first meeting is always with like the purchasing department, because they are looking for someone to make the part. And with some customers, we were able to convey to the purchasing department, like, hey, you need to let us have access to your engineers, because this could change the way you do ceramic parts. And I think this is the moment where we got really successful with it.
But this is also where you're completely right, but this is also where we are still struggling a little bit. I guess me for sure, seeing also customers we have today doing parts. Like, for example, I visited a customer half a year ago, and was saying it was about a thread in zirconium oxide and a counterpart for it. And I said, yeah, we tried now several parts, but we're not yet sure if we want to market it to our customers. So we want to prove that it's really good and reliable. And this is just like, I don't know, we would do 1,000 threads in zirconium oxide, and we wouldn't expect, I would say, more than 1% to fail. So we really nailed that. And actually what you have is this kind of energy and being, words fail me, but it will come to my mind in a second. It's just like go ahead, be faster. So
It's better to be first.
yeah, it's better to be first and to be the best in this particular case. But actually, the adaptation and the speed that this enters the market is relatively slow. It doesn't matter how much energy you put into it. I think we've done everything we could at that time and still do today, but people react cautious and a little bit hesitant. And so we are already thinking about the next or the second to next step. Why I would say there's still a huge potential for that technology to be adapted by many others. And this is kind of, I don't want to use the word frustrating, but I think this is what we feel sometimes. That it's simply not developing fast enough. The one or the other.
I mean, for me, especially in the beginning, it was kind of frustrating because I would consider myself a scientist first and foremost, and I enjoy working on science. Something I'm not enjoying that much is being in a sales conversation. I guess this is like probably every scientist or every technical person can kind of understand that. And in the beginning, when we started marketing this, we discovered really quickly that this is too complicated to explain for a normal salesperson. And we don't really have normal salespersons. All of ours are like they have a technical background. The majority of them used to work really long in technical positions in our company, but still explaining the effects of a ductile regime. And this was hard for them. So in the beginning, I was having like 3 or 4 sales meetings per week explaining this to potential customers.
And especially there is this, you need to have the I don't know if this translates, it's this transfer of knowledge into a specific field. So you know the principle, but still, if you want to be relevant, it needs to be adapted to the customer challenge. And this is the hard thing, because in ceramics, what we see, so a little change also. The material itself has an effect on the whole effect, on the whole thing. Even if it's, you would say zirconium oxide, silicon carbide, it might be, or there will be differences. And this is what you have to keep in mind. So it's a very complex field. And I can still remember, so every sales rep tries to drag you into the sales calls, which is also a nice thing. Yeah, you know, you have a material scientist who's not actually in sales. He's telling you all those things about it. You feel valued, and what he says is super relevant. This is a nice sales tool, unless you are the material scientist.
I mean, I have to say, nowadays it kind of feels like I am in the sales team. Mm-hmm. At the moment, I'm doing fewer sales calls than like a year ago or 3 years ago. But still, for example, I'm attending every sales meeting we have. So it kind of transformed into this one. But I think it's also, like, for my professional development, it was pretty good because I don't want to be the scientist in the lonely tower working on something for 10 years which has no market relevance. I kind of like it that the technology I discovered here with the ductile cutting regime, I think at last count it was something between 8 to 10 machines that are like running that process. So there's like a decent amount of micro HDs out there where people operate a process I discovered, and that is really cool. That's like a worthwhile time spent of my life.
Absolutely. And the next thing is, for me, from a broader view, I would say, this is what I said at the beginning. We want to be relevant and we transfer know-how. And what you also mentioned, at that time when the ductile cut has been discovered, we're thinking about how do you want to commercialize it? Commercialize it already, is that already a bad word? How do we want to use it? What do we want to make out of it? And there was the idea, let's keep it in contract manufacturing, for example. But this idea was off the plate immediately, because I said, that's what we promise all the time. We will give you access at Kern to very relevant, innovative kind of processes and knowledge, and walk the talk, actually giving that to our customers for free. It's what we still do today. And I would say 8 to 10 machines, that's right. I think that a lot more are using the technology today in the one or the other application. And of course, I think it is a very good reason, seeing the potential of that technology, also to adapt that to your special needs, even if you're not in ceramics, you see, okay, working with this company will not just give me that one-time effect of having a new machine that is capable of doing several stuff, but they will continue to develop new things, and I will be part of that. I will have access to it. And therefore, this was really, walking the talk and showing that we do what we promise.
Yeah. I mean, for us as a company back then, it was really hard to, getting that ductile regime working with that crazy cutting speed, that kind of worked. And for us as a company, when we saw this, we had to decide whether we are going to really dig down into it, because proving it once, that's not going to be a marketable skill of the company. And I suggested, being a material scientist, I suggested back then, hey, we should get a scanning electron microscope. And I remember very well the first time I said this to you, you were like, are you crazy, Marvin?
Are you kidding me? Yeah.
Why would we buy we're not a material company. Why would we need a scanning electron microscope? And then I did basically what I always do when I want something bought here. I started whining about it for like 2 or 3 months. And it got so annoying that at some point you just were like, yeah, okay, we're going to order one. And we got like a small entry-level desktop model. It's a Thermo Fisher Phenom XL.
By the way, they were great at that time, so they directly understood what we are doing, and they were very supportive.
Yeah.
So we had some challenges at the beginning, but I think that we've never ever regretted to make that decision to buy that thing. And still to today, it's there, and we are grateful for the partnership that we have with them.
Yeah, they were really accommodating in the beginning because we weren't sure we want to buy it first. So we started renting it, and they immediately made it happen, even though it's not a usual model in their sales process. So that was really cool. And I have to say, I would say from I've now been with Kern for 6 years. And in the 6 years, we bought a lot of metrology equipment for the apps department, for me. And I think this is still the most valuable one we have. It enabled us to dig so much deeper into the process, because with an optical microscope, even if you have like a super high quality one that costs hundreds of thousands of euro, you're limited to, there's like a theoretical limit. It's called the AB limit after the German physician Ernst AB. And it basically tells you the maximum resolution is half of the wavelength you're using. This is the theoretical limit on a perfect device. And obviously in reality, you never achieve this. So in terms of magnification, most microscopes stop at 1000 times magnification, and kind of like 2000 times is very close to that theoretical limit. Now our entry-level SEM easily does 10,000 times magnification. So you get like an order of magnitude more, and depth of field is much better, contrast is much better, so you can really see small details. All the stuff you read about in theory, that like if you do a chip in aluminum, it's going to have shear planes. Well, on the normal microscope, you see a chip and it kind of looks rough. And on the scanning electron microscope, you actually see the sheared planes. So you see the theory is correct.
Hopefully we all now have the REM picture in mind that you published on ceramics and the ductile cut.
Yeah, exactly. And that's kind of like, I mean, that's really cool to have such a device. And I would also think that we are probably like the only machine tool company currently owning one. I know a couple of tool manufacturers that have that, and of course the material manufacturers have scanning electron microscopes, but I don't think another milling machine tool company has a scanning electron microscope.
That is, by the way, also something that we're challenging quite often. If you look at the industry and you see how a process is formed and developed, tool, the machine, the laser, also being able to measure and to detect certain things in the tool, analyzing the tool path, things like that. So there are many parts in the machine and also what you use in the process that have an effect. But usually those entities don't talk to each other. So this is what I find ridiculous. So it's just like, we had, it's many years ago, but we had tools that couldn't be detected in the laser because of reflection and whatsoever. We had material compositions that wouldn't work together, and you just ask yourself, why on earth is the tool manufacturer not talking to the laser manufacturer that is at the end detecting the tool and trying to work together, making things better. They, at least from my knowledge, still to today don't do that. So I feel this is all on our plate. And what made the difference also in this part is not to try to focus on the things that you do, but really to broaden the view and say, okay, we need to look from the beginning to the end. And you see that in contract manufacturing, we are also in the creation of materials. So really in the ceramics, pressing, sintering, because we see it has a big effect. And if you want to control the process, you need to control it from the beginning to the end, or at least you need to know what you're doing. And from my perspective, this is something that also changed the way we look at customer challenges, topics, and perhaps we have some time to talk about the workshops, for example.
Yeah.
This is something that is now in our DNA. It's not just look at the machine or say, oh, it's not our problem. It's part of it's tool manufacturer's problem, or it's tool holder problem, or it's automation or flat coolant or whatsoever, and we don't have to care about it. No, it's the result that counts at the end of the day. It doesn't matter what it takes. We will dig into it also if it's not in our very focus of the things that we are doing usually.
Yeah, I mean, I'm totally with you that controlling the whole process, especially on like high-end parts, is really important. And I think what you get with pretty much every machine tool company is you can call for support. And if for example, you have like one flaw on your part, let's say you have too much deflection, you're milling aluminum, you have too much deflection, and you call the apps department of a machine tool company, they're probably going to tell you, yeah, increase the cutting speed, it's going to get better. And then this feature works. But on the very high-end parts, sometimes customers, I mean, our customers are really good at what they are doing. And they've looked really deep into their process, but at some point they arrive somewhere where they can't improve anymore. And something we offer to our customers is that we kind of support them there. And one way we are doing this is having a workshop with me here at Kern, because, well, we have the equipment here at Kern. And then
tons of equipment,
yeah. And then we kind of look at the whole process in a holistic way. So we start by analyzing their material, we start by analyzing their tools, talking to them about how they are manufacturing this. We recently had, and I think this is a really good example. We recently had a customer workshop in the apps department. Not yet a customer, but maybe next year. And it was like a molybdenum part. And
hey, isn't it called molybdenum? No. Molybdenum? I think then the measure always says molybdenum.
Yeah, okay, well, but the Americans also say aluminum. So, yeah. So
and Hermele.
Kern. Okay, yeah. We need to stop laughing at, yes. Okay, so, and usually the problem with this material is if you mill it, your surface roughness is never going to go below 0.2 microns. Never. No matter what tool you take, no matter what you do, it's going to stay at that value. And this was also kind of like the result of that workshop. We manufactured the part, customer was kind of happy, and I was like, ooh, can I have a chunk of that material? Because it's devilish expensive. Like a 50 millimeter 2-inch disc, 10 millimeters tall is like $500-600. It's enormous how expensive that material is. And that potential customer was nice enough to give me one of these discs to, they were like, have fun playing around with it. I was like, yeah, I'm not going to play around with it. And we basically managed to do something similar to what we did in ceramics. I did like systematic research into changing the way the chip is formed. Because the way chips are formed in molybdenum, there's a reason you arrive at Ra.2 with that material. And after working on it, I actually managed to change the mode of chip formation. And the result was with like regular toolings, you don't need specialized tooling for this. It's just like you need to know how to change the feeds and speeds to arrive at this. We managed to get a surface finish of 0.05. And 0.05 is kind of like the requirement for like ultra high vacuum applications for semiconductor parts, which is the main use of molybdenum as a pure material. So now I think next year is going to have some really exciting projects, because this is once again something you couldn't do before. People were so used to it that their drawing either involved this surface needs to be polished, and polishing has a lot of limitations. It is super expensive. And now we could kind of offer them a CNC-based milling process that gives them the final surface specification. And this is massive. And this is kind of like, this is something customers of ours can also try to achieve. They can kind of be like, hey, we have this really huge problem. Would you be willing to work together on this? And then we do a workshop with them and try to change the way something is happening.
So when you talk about it, it sounds so easy in just a few days or something like that. We all know that is not the case. I was just saying, at the one or the other point in several process, we also have been lucky. So like every other thing in the world that is relevant, a bit of luck is always necessary. But besides that, so if we're looking into a metrology room in the meanwhile, and what we are right now thinking about to add to it, so there's also a lot of equipment, effort, and so on needed.
We already added to it.
Yeah?
Yeah, Sebastian, I sent the order out last week.
Very good. Okay, very good. Yeah. What are we going to get?
Yeah, so basically we're going to get the mother of all electron microscopes. We've been very happy with our small desktop model, but resolution on that one has a limit. It's usable to 15,000 times magnification. And we have a couple of research projects going on, very top secret research projects, where we kind of need to dig deeper. And we bought a Zeiss Gemini ZEM 560, which is like the highest resolution scanning electron microscope you can actually buy at the moment. It's like every dream technology of scanning electron microscopes put into one device. It has like a field emission gun, which is like 10 times brighter than the electron source in our SEM. It has like 10 times lower noise. Then it has like a magnetic and electric immersion lens. So the whole sample is immersed in a field, which increases resolution another order of magnitude. And all of this arrives at like sub-nanometer resolution over the whole acceleration range of the microscope. So it's a massive invest for our company. It's also a huge device.
Will it fit into the room?
It will fit into the room. But I think something I didn't tell you yet is they're going to come in and measure the room for like magnetic fields. And then we probably need to do like a magnet field compensation in that room. So get your construction team ready.
Sounds easy.
Yes, exactly. No, but I mean, like, I think this is like the scanning electron microscope you have at high-end material development universities. I would be surprised if there are more than 10 or 15 of these in Europe. And next year we're going to have one. I think this shows our willingness to invest into this technology. And I mean, at the end of the day, this is not knowledge we keep for ourselves. This is not that our contract manufacturing becomes more profitable by this. But the majority of my work with these devices goes to customers. They can call and they get the process, they get help.
And I think that's the beauty of it. But what I can tell out of my position, that is also always a challenge. You know, at some point you might come to the resolution and say, okay, we just do what is relevant. We don't do what is just scientifically interesting. And the topic is to decide between the one or the other, and also allow to say, okay, we spend time and money in things that might not commercialize, that might not pay out. And this is also something that you or we have been lucky with, respectively paid a lot of attention to, which comes a lot of your personality, to say, okay, we want this to be relevant. And you're saying you don't want to be in sales. So Marvin's machine is right the first one when you enter the application department. In the meanwhile, there's a lot of stuff around. So I think we got a vitrine last week that is now full of parts. So this has not been ordered or wished by myself, but this is coming out of your personal motivation. So I think this is also something where we make a tour today. And you've had an office here, which you're barely or not using at all. So I think somebody else is sitting at a place right now, because you're sitting outside side, and when we come by with customers or whomever, you always have time to talk about those things and make an elevator pitch on the one or the other.
I would say I always take the time.
Yeah. Yeah. Okay. Let's be precise on that too. Yeah. Okay.
I mean, I enjoy that our company is successful, and I mean, at the moment, German market is in really rough times. I think 2 days ago, the last major German machine tool company went into short hours. Like all of them are struggling at the moment, and I don't see short hours at Kern at the moment. So we are doing really well. And if a customer comes by and they are interested in technology, I mean, we sometimes have purchasing departments come by and I just say hello and I smile and I wave and I'm like, yeah, I'm Marvin. Hi, nice to meet you. But if we have customers come by this week, we had a potential customer from Italy visit, and they were really interested in the technology. And I was chatting to them for like 5 minutes and we're like, oh yeah, does your machine have this function? And an apps department machine was currently running with their parts, so we couldn't show it. And I was like, yeah, give me 5 minutes. I'm going to remove my setup from my machine and just show you the functionality. It's about parameter switching. And that is really nice that you can have that technical discussion with the customer and show them like a super cool function of the machine. So I'm okay with my research machine being in the front of the building and being like where every customer enters. It's fine. It's nice to talk to them.
In that subject, so what you've done, and out of intrinsic motivation, I haven't understood it completely so far, is you also do all our fair and exhibition parts that we do. We have a set usually of 10, 2 or 3 new ones, 2 or 3 old ones get pushed out every year, 2 or 3 new ones come in. Perhaps you tell us a little bit about that. So where are the ideas coming from, and perhaps you have the one or the other example that you can share how you do things.
Yeah, I think there's two sides to our sample parts. The first one is the easy one. Basically, it's sales requests. So our sales managers are like, hey, Marvin, you do all the sample parts. I'm like, yeah, I don't know why. And then they are like, we want this. So, for example, one series I did this year were like these POSI drive screw bits. And the original one was from tungsten carbide. And this was a sales request because our Austria sales manager, Thomas Mauer, he was like, hey, Marvin, I have so many potential customers who are like stamp and die. Could you do another stamping die? And then I looked at like, okay, what are shapes that get stamped nowadays? And if you have like a Torx profile, that's like an expensive screw, and a complicated profile, this gets milled. But if you have, for example, that POSI drive, that Phillips profile, these are actually in like normal metal screws, just get stamped. So you have like the flat screw head, and then you just stamp it with a carbide stamp. So this is actually a real part. This is like a screw head stamping die. And I manufactured like the first 3 ones, so salespeople have some to take with them to customers. I was like, this is a really interesting shape. Interesting in the sense of you're able to manufacture it pretty quickly, like 1 or 2 per day, even in like a prototype state. But it has interesting shapes. It has freeform surfaces, it has sharp edges, it has rounded edges. It has like singularities. So singularity is a point on a freeform surface where for the machine movement there's 2 solutions. Basically, think about you have like a straight shape, and you tell the tool, okay, I want an angulation of 20 degrees in feet direction and 30 degrees counter to the feet direction. This is easy on a flat surface. But now you arrive at a point where basically you have like a 90-degree bend. At this 90-degree bend, this is a singularity, because when the machine moves around that corner, the 30-degree sideways lean could be, let's say, in X plus direction or in X minus direction. So the machine has to decide what does it take. And especially if you have like head-head kinematics, so the head is swiveling, this sometimes makes the machine turn and turn and turn and turn. One of the reasons we decided to go for like a table kinematic, because then the singularities are more easily resolved. So from a geometry perspective, this is kind of like an interesting part. And I was like, stamps are sometimes made from ceramics. So, for example, for like dog food cans. So if you have like a can for drinks, like a beer can, they are made from aluminum nowadays. But animal food, they are actually like sheet metal from like iron materials. And they are more abrasive, and sometimes they are actually now to stamp the little lever with which you can open the can. They are actually sometimes stamped with alumina oxide. And I was like, okay, let's do this stamp in alumina oxide because I had a chunk in the correct size lying around. And it turned out really nicely. It's like flawless, no breakouts on the edges, well, because of ductile milling, and the surface is really smooth. It's like, this is cool. And then I think Stefan Zeller, our sales manager for Eastern Switzerland and Baden-Württemberg, he walked by. He was like, could you actually do this in hard steel as well? And I was like, I think so. And then I took like a chunk of Elmax, which is like a high quality mold steel, which also gets used in stamping dies at 64 HRC, and I just mirror finished it on the machine. And then my imagination kind of went wild. I took a piece of silicon carbide. Then I was like, you could probably also do it in glass. So I took a piece of Cerudur and made one. And then I uploaded all of these on Instagram, and people were asking for new materials. They were like, hey, can you do it in this? And I think now we have like 12, 15 different materials.
Fire and whatnot, yeah.
Yeah, and sapphire is a good point. We have them ranging from like, the softest ones are like copper, brass, carbide. I don't think I've done an aluminum one yet. But there's like, so if you look at the hardness scale, a really good scale is the Vickers scale. So not Rockwell scale, but Vickers scale. Because that one can basically measure everything from the softest possible material to the hardest possible material, which would be diamond. By definition, diamond is 10,000 hardness Vickers, and something like tungsten carbide is around 1,000 hardness Vickers. And copper is at like 120, 150, so it's like really soft. And sapphire sits at like 3,500, which is nearly the hardest material besides silicon carbide, CBN, and diamond. And that machine, I mean, this was my machine who manufactured these parts, and it manufactured all of these parts. And obviously there was adapted strategies for every part, there was adapted cutting speeds, adapted tooling for every part, but you have a machine that was able to manufacture, without changing anything on it, everything. From softest possible mirror finish to hardest possible material ductile regime. So I think this was a really cool sample part. So yeah, the process is sometimes there's like a sales request, and then very rarely I answer these sales requests, do a part. A lot of it is also, and this is like the second side to our sample parts, is strategic work. So there's strategic markets where I decide, and this happens a lot, I would say, in conjunction with you in our like weekly meetings where we discuss where do we want to set a focus for the next year? Like what industries are important to us? And then I think about what parts do they need. So this year we did a lot of work for semiconductor. We did a lot of ceramic parts that are found in semiconductor work. We did like a Cerudur readout head with very fine features, very high flatness, because this is like a semiconductor part. We did a wafer chuck from silicon carbide with like 50% quicker cycle time and 1 order of magnitude better surface quality than the existing industry standard process for wafer chuck. I think next year we're going to see a cauterite linear motion stage appear. So these are like strategic parts where we take a not really a real part. I mean, obviously we don't take customer parts and mill customer parts, but it's geometries we know exist in customer parts, in geometries the industry needs, where a purchasing department or an engineer from that industry can identify themselves with, where they're like, hey, this was a struggle for us.
I think this is also an important point. So on my first fair that was in Geneva, it was EPHJ. EPHJ. So our French, so he always goes crazy when I try to pronounce it in French. In the meanwhile, I think I'm pretty good at it, so he will let me know. And what we had is a big vitrine with, I don't lie, 120 parts. And what you often do in the industry is, we have a scroll wheel, and we have a scroll wheel there. So everybody who's in scroll wheels, they see, Kern is also doing that. You have injection nozzles or something like that. And I say, okay, if you are in injection nozzles, this is a relevant machine. This is the message that manufacturers want to send. And I'm so glad that we went away from this having everything like a mid 19th century supermarket, just having everything that might be relevant, but nothing to a certain profession. And seeing that, for example, the POSI drives, somewhere we show the general principle, the material, the abilities we have, but the transfer to your technology, this is what you should do. And this shows this is not a standard part, not a commodity. And I think the not being in a commodity is a very important thing those days. So that's what we don't want to be in. And the real, I should say, parts that you describe. So where you have applications that are made for a certain application. So we do in fields where we really make a difference. They're not that easy. So we don't want to show we can also do it, but what we want to show is we can do things that you couldn't done before, or in a totally different, by far more affordable way. We can do it in a better quality, in faster cycle times, or we found something that is relevant. And I think that is the most important thing. Show relevancy. It's not about selling a machine with those parts, but it's really about educating and creating the awareness that we've developed things that might be relevant for the future.
Yeah, I mean, for example, with the wafer chuck, there's, I would say, 5 companies in Europe at the moment doing wafer chucks. And all of them have like this well-kept secret on how they manufacture it. And then there's kind of us, where you could actually give Simon a call and be like, hey, I want to manufacture wafer chucks. If I buy a machine, are you going to tell us how to manufacture it? And we're going to be like, yeah, sure. It's going to be better than the existing process. And I mean, yeah, it might be difficult to get on the suppliers list for this wafer chuck, but it's just like, you could buy a machine and get the know-how to make a part that only 5 companies at the moment know how to make. And it's not their process, it's a superior one. So I think this is really nice. And this is something we have been showing at exhibition fairs, and what our sample parts are aiming for, to show you that we are like a superior technology partner.
Yeah. And I think that is also what we discussed earlier, or what you already mentioned, that has been in the last couple of years, and is as well this year. And also Kern needs to put more energy into the market than we usually have to do. But we're happy with this year. We are happy with our orders and customers and things like that. And the reason for that is that we exactly offer that also to customers that want to make a difference. And it's not just like, if I buy a Kern or if I buy something else and I compare on price or whatsoever, if we cannot stand out in performance, and if we cannot achieve the price that we need for all the efforts we make and for the quality of the machine. So today, and I have to admit it has been different at the very beginning when I joined the company, but today I say, and it's good. If something else works for you and you're fine with that, that's good. We're not going to fight tremendously on price because of that. Because if the value proposition doesn't hit you and is relevant, then it's good to buy something else. We're happy with that. It took a while, I have to say. So.
Yeah, I mean, I usually think like, oh, everybody should own a Kern. They are so amazing. And whenever I think that, I have to think back to our former Northern Germany sales manager who said, not everybody deserves a Kern, which is still the hardest statement ever. But yeah, the reality is our machine is a good fit for a lot of people, but sometimes it isn't. And I think we are doing very well nowadays to be like, okay, get that machine, then it's okay. Come back when you have a project where our machine makes sense.
Yeah, very good. So Marvin, perhaps I don't know how much time we have left, but can you share something that you are planning to work on in 2025? Something that's not top secret.
Yeah. I think 2025 is going to see that before mentioned Corderite linear motion stage. Corderite is a really cool material. It looks horrible. It's like mint green. So aesthetically pleasing, no. It's a ceramic material, and it basically has the stiffness and Young's modulus of aluminum oxide, which is really exciting for mechanical applications that need to be precise. But its thermal expansion coefficient is also very close to Zero-Dur, so nearly zero. So it's like a wonder material. Lead time is horrible. It takes like half a year to buy it. There is exactly one company making the good stuff. That's Kyocera in Japan. It's also devilish expensive, but you can make really cool parts from it. And I have the material here, and I think 2025 is going to see me making those linear motion stages, and it's challenging to manufacture. So I think this is going to be sample part wise what is planned for like first half of the year. I think we're going to see more advances in ceramics. So our scanning electron microscope is arriving in, I would say February, probably, our new one. And one feature this one has is it can detect crystal orientation, which is really advanced. And we started to notice that on like ceramics, crystal orientation has some influence on the behavior, on how you mill it. And I think this is going to be something we're going to publish because I usually think there's like knowledge-wise, there's two things. Company IP, which we kind of need to protect a little bit, which is reserved for our customers. And then there's stuff which is just like so annoying to conquer that I think the whole of humanity should profit from it. One example is next year's USPM, European Society for Precision Engineering. I'm going to hold a talk about ductile milling of Zero-Dur class ceramics. And yeah, this is knowledge we could keep for ourselves, but this was a like huge pain. It took me like 4 months to discover how to do it. And I decided like, yeah, I don't want anyone else to suffer through the same process I did too. So I'm just going to tell people how to ductile mill Zero-Dur at next year's USPM. And I think with the crystal orientation, this is also something. And I'm really excited to like work on crystal orientation. I see a lot of potential in sapphire, that by adapting your tool path to the crystal orientation, you're going to have better results. So I think, yeah, that's two of the projects I'm willing to talk about for next year. Very cool sample part coming, linear motion stage, and crystal orientation based milling.
Sounds exciting.
Yeah, maybe. Okay, just like you said, Simon, we are nearly at the end of our talk. It's time for the question. And you're not prepared.
No, I'm not prepared as always.
So, Simon, as I've been speaking for the majority of the time, now you have to talk. Tell us something that happened to you since our last podcast. Can be something good, something negative, something that happened at work, something that happened at home.
Something.
Shoot.
Yeah. So I'm a positive guy. So there's something negative. And I couldn't think of something. So something positive that comes to my mind. So I had a bad injury at my on my arm. I don't know if you talked about it. I had an external fixation and things like that. That was a really ugly thing. And so the chances of total rehab and being able to use it in the former way was rather small. And last week with some friends, I went to Tuscany to have 3 days of hot enduro. And actually I was super afraid that my right arm is going to break at the first day. But actually we had 3 wonderful days. The weather was super nice. We did a lot of kilometers and went everywhere in the mountains on very steep kind of, I should say, paths where we drove, and everything was fine, and I had a wonderful time and was super glad that at the end now, after 1.5 years, so everything seems to be in the last step of being back to normal. So I'm very grateful about that and happy about the 3 days I spent there.
That's really cool. I saw the pictures. Looked like a really good boys trip.
Yeah, it was. They are all getting old, so We are not as drunk as we used to be, and no, but it's more about the fun, and it's dinner and lunchtime is getting more and more important, as it seems.
Very nice. Cool. Okay.
Hey, what about you, Marvin?
Yeah. I think I had a really good weekend the last weekend. I used to, I mean, this was my step into mechanical engineering. I used to tinker a lot in my free time, like build machines. So 10 years ago, I was building like a Delta 3D printer, and then a laser cutter, and then a small milling machine, and then a small CNC lathe. And at some point, when it became my profession, I stopped having the motivation to tinker in my free time. But I've been longing for like a more solid microscope stand for a long time, and there's not really something you can shop that would be sufficient to my quality requirements. So last weekend I decided like, hey, I really want to spend a whole weekend milling. And I basically manufactured the microscope stand in one weekend. It's like 140 kilograms of aluminum and granite.
This is crazy.
It's the mother of all microscope stands. It is like ball screw driven, and it turned out super nice. And what was really nice about the weekend was, I would say the parts were a little bit on the large side for the Kern. Like maximum size you could fit in and still do all of the features. And the whole weekend I did like a whole Euro pallet container of aluminum chips on one weekend, and the machine just worked flawlessly. And like every dimension was within 5 microns, and it was just like I think like Sunday afternoon, the feeling just happened in me that was like, this is a really good machine. It's a lot of fun to just do like parts on it. So that was a really good weekend.
No, your very old machine. Sebastian, gonna hate you for that. Oh, thank you very much, Marvin. This was very interesting. Big fun today.
Yes. Thank you, Simon. See you next time. Bye.
Bye.